Hello, and welcome to the makeup video for the Hydrologic Cycle lab. So this lab starts on page 49, and we'll be discussing how the water cycle, or the hydrologic cycle, interacts and basic information around that. So this is a sort of follow along lab. There are several questions throughout with the key on, or sorry, the worksheet page on page 53. So we'll go ahead and get started. So water plays a major role in shaping the Earth's landscape. I know we've discussed this quite a bit throughout the lab and within the course itself. So it exists in various forms in the environment. Liquid as rivers, oceans, swamps, and rain. Gas and water vapor and clouds. And solid as ice, snow, and glaciers. So that picture in the top right here, you see this river cutting through all these different layers of rock. So on a short time frame, you may not notice all these little differences, but on a geologic time scale, water can massively shape entire environments and landscapes. So the first question is to develop a model of the hydrologic cycle. There's space at the top of page 53 so that you can do it on your own, but I'll just go ahead and start walking through this just so we're all on the same page. So included in the diagram are these reservoirs: oceans, atmosphere, glaciers, surface water, which is rivers and lakes, and then groundwater. And then there's also pathways, so how the water moves between these reservoirs, which for the hydrologic cycle as a whole includes evaporation, transpiration, which is return of water to the atmosphere from plants, and then precipitation, runoff, and infiltration, which is the movement of water from the surface to groundwater. So just working from this image here, that first reservoir in the right here with the black number 1 is the atmosphere as gaseous water. Number 2 on the bottom right are oceans. Number 3 is groundwater. Number 4 is the surface water, which here is shown as a stream but also includes lakes. And then 5 is glaciers. And these are all the different reservoirs in the hydrologic cycle. As far as the pathways for them, evaporation happens when the water heats up and moves from a liquid to a gas. So here, moving from the ocean to the atmosphere as evaporation. This does also happen over surface water as well, but just for the sake of simplicity and ease here, it's just shown over the ocean. Second one is transpiration. So as plants uptake water from the ground, it's not just indefinitely held in there. Otherwise, every plant you'd see would be slowly swelling and getting larger and larger as it absorbs more and more water. The water that they don't use up throughout their different systems and processes involving growth and that sort of thing uh, gets transpired back into the atmosphere. So it's still liquid water moving to a gaseous state into the atmosphere, but it's facilitated by plants here. So condensation is when you take gaseous water from the atmosphere and condense that into a liquid, and even further as uh, ice and snow, where it can fall down further. Sublimation is when you have ice, such as from glaciers, skipping over that liquid phase and just going from that solid ice phase directly to a gaseous phase into the atmosphere. So it might not be something many people are aware of, but if you left an ice cube out on the sidewalk, even if, or let's say just on your windowsill outside, and it stayed well below freezing for, several weeks on end. That ice would still eventually disappear, not very quickly, but it would still disappear from that sublimation process. Basically, similarly to how the sun heats up liquid water and causes it to vaporize into gas into the atmosphere, like we see over surface waters and oceans. That similar process happens directly with ice as well, but skips over that water phase because it's so cold in the air. The air can't really sustain, the environment can't really sustain a liquid water. But if those molecules of water in the ice get energized enough from the sun, they can still sublimate into a gaseous state. So precipitation, of course, is when you have that rain and snow going from the atmosphere, that condensed from the atmosphere down to the earth, either into surface water, lakes and streams, or this also occurs over the ocean, and really anywhere over the surface of the earth. Moving from surface water to groundwater, that pathway there is infiltration. So that's when that surface water moves through the surface and into the ground. Runoff, of course, is when you have that surface water moving along. You can see that in streams, but another example of runoff is when you have rain moving down large hills or just any slanted surface. Before it infiltrates into the ground, that can still move over the surface as runoff. And then the last pathway we have is groundwater flow. So that groundwater, once it's infiltrated underneath the surface, it doesn't just stay immobile. Groundwater can move as well. They're similar to how rivers and streams move downhill. You also can have a slope in groundwater, which allows it to move uh, larger distances as well. Eventually, in many areas, that can feed directly into other surface water systems or directly into the ocean, as is shown here in this diagram. For question number 2, looking at your model, which reservoirs do you think would provide fresh water that would be available for human consumption? And at this time, which freshwater reservoir do you think is the most abundant? So this question specifies freshwater. So the different reservoirs we have here that are freshwater that we can readily use would be glaciers, surface water, and groundwater. The atmosphere, while it contains water, fresh water, it's not readily available for us to use until it's already precipitated down to other reservoirs. As far as which one is the largest, it might actually surprise you. So surface water, since that includes lakes and streams, just as an example here, the city of Bloomington uses surface water from Lake Bloomington as their primary municipal water supply. The town of Normal actually uses groundwater. There's wells dug into the Mahomet Aquifer, and they pump their groundwater from that. But the largest reservoir of fresh water is actually glaciers. Glaciers, frozen water around Earth's surface, is actually the largest reservoir of fresh water on the Earth. So it can be kind of surprising. With how much water is on the surface of the Earth, there's only so much of it that's fresh water, and even less is readily available as liquid water from surface water reservoirs or groundwater. So the water cycle involves the constant flow of water from reservoir to reservoir through pathways. Just to reiterate here, reservoirs are a place of temporary water storage, so oceans, atmosphere, glaciers, surface water, and groundwater. The pathways, also called fluxes, are the movement of water between reservoirs. So that's the pathways we spoke about: evaporation, transpiration, precipitation, runoff, and infiltration. So if you're unfamiliar with the term flux, really what that means is just a transference, a movement of something. And that's something that can be measured. Oops. Okay. So just as another reference here, if you want, you can take a screenshot of this, just so you have it for reference in your notes, or if you've already filled this out on page 53. So 3 through 9. Oh. So there's a diagram on page 50 as well for these next few questions. But as water vapor condenses, heat energy is released to the atmosphere. So that's question 3. So for some background on this, you can classify any scientific system as an open system or a closed system. A closed system is really an ideal system where at most you might have some energy transferred to adjacent systems, but all the matter, all the mass in it stays the same and doesn't leave. Open systems involves the transference of both matter and energy into and or out of the system. So in the case of hydrologic systems, that matter is going to be water in all of its forms, solid, liquid, gas, and that can be transferred between those different reservoirs. So the energy that supplies these and moves the hydrologic cycle along is largely supplied from the sun. Some areas there can be a little bit of energy introduced from radioactive decay inside the earth, but ultimately the hydrologic cycle is largely driven by the sun. So this energy is also transferred between different hydrologic reservoirs, honestly carried by the water itself, as it can be part of that as well. So question number 3. As water vapor condenses, heat energy is released to the atmosphere. What do you think happens to the heat energy? So ultimately, as that water vapor condenses, that heat energy gets released to the atmosphere and warms the atmosphere. Pretty straightforward. Number 4, if the Earth warmed and there was more heat energy available, would evaporation increase or decrease? So evaporation would increase because you have more heat energy available to drive that change from liquid to gas. Number 5, how would a warmer Earth alter the hydrologic cycle? So a warmer Earth, as we've already discussed, that would increase the evaporation. So with that increased evaporation, you have more water in the atmosphere, which could also drive more precipitation. That warmer Earth would also cause glaciers to melt, which is an environmental change that we have seen as climate changes. And then ocean level, sea level, actually can rise as well as more liquid water is supplied to that reservoir. To help reinforce these concepts, we'll watch a brief video illustrating the water cycle experiment.
Demonstration experiment on the water cycle. We're going to make it rain inside, and that's a cool thing. And it may seem like a lot of materials. It's very simple, very user-friendly, very easy, and we can make it rain inside. We want kids to be able to see the water cycle work. So I have a pan full of water. I heated it on the burner. I don't know if you can see the steam coming off. We wanted to speed up the evaporation process. So instead of the sun heating the water from above, the coil is heating the water from below, making it evaporate. So evaporation, easy. But the cool part about evaporation is it cleans and cleanses the water. So I want to make this water dirty. I could spit in it, things like that. I'm just going to put some red food coloring, some blue food coloring. You could put in dirt, you could put in vinegar. I'm going to put some salt in. You could put in sugar. You can see plenty of salt. And I have a soupy, dirty mess in there. I would not want to pick that thing up and chug it down. It's dirty, but that's what's cool about the water cycle. We can take this mess and purify it, clean it. We need all the water cycle to do it. So here we go. All of that liquid in there is starting to evaporate. what I need to do is I need to be able to condense that water vapor in this air. How do I do it scientifically? I need something cold, and I need the water to condense onto something. So I have this pan. How do I make the pan cold? Put some ice in it. So let's rip the bag open. Let's put some ice in. The ice is going to melt, form a nice cold layer of water. Now, I'm going to hold my cloud, my layer of cold air, over this water vapor. And you're going to see this pan actually start to fog up. What's going on? Well, as that water vapor is hitting that cold pan, it wants to condense back into a liquid. And it's starting to condense into a liquid. And as more water vapor hits, all of those tiny droplets of water get bigger and bigger as more water condenses onto it. You can actually see it. And we're going to give it some time, but actually enough water is going to condense on the bottom of this pan. It's going to rain. It's going to precipitate. And the cool thing is, I'm going to lick this pan. It's not going to taste like salt. Why? All the dirt's left down in the pan. That's the cool thing about the water cycle. It cleans all the water. It's an amazing design. So to show you that the water on this pan, we brought in a little light, and we're going to angle the dish. I normally wouldn't do this, but just so you can see the water condensing onto the pan, and you're going to see it precipitate. So here we go. Let's angle this. Try to keep the ice in the pan. And if you'll see the water dripping down, it's not dripping, it's raining, folks. That's the scientific term. We have water evaporating, hitting the cold air, or the cold pan, condensing onto that. That water droplet gets so heavy that it rains, it precipitates. It's the beauty of the water cycle. Thanks for watching.
Okay. So what happens to the water when the heat is added to the pan? The energy heats up and evaporates the water. Number 7. Where does the water that condenses onto the pan, where does that water originate? That originates from the pan of water that's heated up and evaporates into gaseous water. That water vapor then eventually condenses on that pan filled with ice. So for 8, as the water condenses onto the ice pan, heat energy is released. Where does that energy go? Well, since that's condensing onto the pan with ice, that released energy is being absorbed into that cold pan. So that released heat energy will warm the pan and help to melt the ice. And number 9, does the experiment represent an open or a closed system? So that actually represents an open system. Because nothing's holding in the vapor, you can have matter move outside of it. And you could make it a closed system if everything were completely contained, so no matter, no water is leaving, but because he's just doing it in an open room, fully exposed, that's going to represent an open system. So moving on to the water budget. The water budget ultimately is based on the conservation of mass. So as in any given system, you can have in an open system anyway, you can have water, or you can have mass moving into and or out of the system. If those are the same, those are balanced, then you're not having any major change to the system overall. But in open systems, that's often not the case. So as a representation here, we have that delta S, which represents a change in the storage. So specifically applying this to hydrologic reservoirs, so like the ocean, atmosphere, anything like that, you have inflow of water mass into the system. You can subtract the outflow of water mass from the system, and that difference will equal the change in storage. Either it's gaining or losing water if those aren't in perfect balance. Now, the units for this would be a mass per time. This can be converted to a conservation of volume, because on the surface of, in general, Earth surface environments, water is typically within a fairly narrow range of um, states and conditions, so you can assume a generally consistent density of like liquid water, for instance. So if we're looking at liquid water reservoirs like surface streams, lakes, the ocean, or even groundwater, um, you can change that density. You can change that conservation of mass into a conservation of volume by utilizing that consistent density. So, question number 10, what is the definition of density? Density is just a mass per volume. Uh, so if you take that mass equation and divide that by density, you're left with a volume. So, and that's how we can get that conservation of volume equation. So for 11, how can density be used to transform the conservation of mass into a conservation of volume equation? You just divide it by a consistent density. Number 12, why would we want to work with a volume rather than a mass? Well, that one's actually pretty simple. If you look at a lake or a stream, it'd be very difficult to actually weigh out how much water is in there. You know, you can't just pick up a lake and put it on a scale, but it is a lot easier to figure out the dimensions of a lake or a stream or any liquid water reservoir and then work with it as a function of volume. So the volume of for conservation of volume, the units we'll be looking at with that will be a volume, which is length cubed over time. So for the water budget equation, looking at that conservation of volume again, you have that delta S is the change in storage in a reservoir. You have I sub V as the inflow of water volume, so that's a flux, and then minus an outflow of water volume, once again of flux. So that change in storage is the change in the volume of reservoir. So that's going to just be a volume, where per time in some cases, but ultimately if you're looking at a specific time scale, that kind of cancels out. So 13, looking at the ocean, formulate a water balance equation. What would be the inflows and what would be the outflows? So let me switch programs here. All right. Okay, so if we're looking at the ocean, you can reference that hydrologic cycle to figure out what pathways are moving into or out of it. So first, we have a change in storage, and then let's figure out those inflows. If you look at that hydrologic cycle diagram, let me go back a few slides here. So flowing into and out of the ocean, things flowing into it, you have runoff, then you have groundwater flow, and then you can also have precipitation. So inflows, we have precipitation, you have runoff, and you have groundwater flow. And for the outflows, there's really only one for the ocean, and the main one there is evaporation. So we'll just denote that with an E. While there are plants in the ocean, most of them, if not all of them, are typically going to be submerged, so any change from transpiration you wouldn't really see because it's already self-contained into that liquid water. So to generate that water balance equation here, that water budget, you have that change in storage, and that's equal to your inflows. So precipitation plus runoff plus groundwater flow minus your outflows, which is just evaporation. So that's our water budget equation, our water balance equation for the ocean. Number 14, using the values from Table 1, which is at the bottom of page 51, determine what is the total flux leaving the oceans. So that's really looking at what is that evaporation out of the ocean. According to that table, it's that first line there. Evaporation is the pathway. The source is from the ocean to the atmosphere. That's about 505,000 cubic kilometers per year. So that's quite a bit. Number 15, using the values from Table 1, determine what is the total flux entering the oceans. So you'd look at this precipitation. So the pathway is precipitation from the atmosphere into the ocean is 458,000 cubic kilometers per year plus runoff. So runoff from land to the ocean is 45,000. And then groundwater flow. So where is that listed? So it's listed weird. It's not listed correctly, but it's that last line on that table 1. So runoff is what it says. From the groundwater to the ocean is 2,000 cubic kilometers per year, which is 505,000 cubic kilometers per year. So the two numbers from 14 and 15 should be equal, and as you see they are. 505,000 cubic kilometers per year are leaving the ocean as evaporation, and 505,000 cubic kilometers per year are entering the ocean through precipitation, runoff, and groundwater flow. Number 16, what would happen if the amount of water entering the ocean was different than the amount leaving it? So to answer this question, you can just look at your water budget equation. So here, if these were not equal, well, as they are now, you have the same amount going in, so change in storage is equal to 0. But if the inflows did not equal the outflows, then you would have a change in storage that was not equal to 0. So if there's more water flowing into the oceans, that's going to be a positive number. If there's less water entering the ocean and more leaving the ocean, then that would be a negative number. Okay. So 17. Complete Table 2 by filling in the correct reservoir with the appropriate data. The possible reservoirs are oceans, groundwater, surface water, glaciers, and the atmosphere. So I'm not going to sit here and make you work through that all on your own. So if you look at that table, you have a reservoir with 1,420,800,000 cubic kilometers in it. That one is the ocean. That is by and far the largest reservoir we have. Next, you have the smallest with 12,900 cubic kilometers in it. And this might be surprising, but that one's actually the atmosphere. So the atmosphere only holds so much water. And because of the different environments it's in, that number isn't going to be the largest. Third one down is surface water at 189,000 cubic kilometers. Then groundwater at 10,546,500 cubic kilometers. And then the last our last reservoir shown is glaciers. With 24,364,100 cubic kilometers. 18. From table 2, what is the total volume of water in the water cycle? So if you look at that number and total all these up, it works out to be 1 billion, or sorry, 1 trillion 455, or sorry, 1 billion 420 million, sorry, 1,455 1,455,912,500 cubic kilometers per year is the total volume of all the reservoirs on Earth. So as you can see, that number is largely dominated by the amount that's in the ocean. If you didn't have the oceans, we'd only have a tiny fraction of water on the Earth. And even beyond that, looking at the remaining reservoirs, the atmosphere is inaccessible, but it's also quite small for the most part. And the three freshwater reservoirs that are accessible to humans are just a small portion of the overall water available on the Earth, with most of that being contained in glaciers and then groundwater. So while many cities use groundwater as a supply source, uh, surface water from lakes and so on are also very common, but you can see that's not a very large portion. So, it'll vary. From table 1, what is the total annual flux, inflows, and outflows? So, 19. Total inflows and outflows are 1,205,000 cubic kilometers per year. You just add up all those fluxes from table 1. And then what percent of Earth's total water volume is in flux each year? So we have that total volume that's in flux, and then you divide that by that total amount of what's available. So that's the 1,455,000, or sorry, 1,912,500 cubic kilometers. And that works out to be about 0.08% approximately. That's how much water is actually in flux each year. So only the tiniest portion of water actually moves throughout the hydrologic cycle each year. And then 21 reservoir. Okay, so next we need to look at residence times. So residence time is the amount of time water will spend in a reservoir. More scientifically put, it's the average amount of time the average water molecule will remain in a given reservoir. And that's basically, you divide the volume by the flux. So if you look at volume, that's straightforward. That's going to have that volume measurement. And then flux is a volume per time. So volume divided by flux. And your flux is a volume per time. So if you plug that in to here, volume divided by a volume per time. That's equal to volume times time over volume. Volume cancels, and you're left with residence time. So your next step would be to calculate the residence time of each reservoir. So on table 2, basically what you find is that oceans, the residence time is about 22,800 years, whereas for the atmosphere, the residence time is about 0.03 years. Surface water, with all the fluxes going in and out, residence time is approximately 1.57 years. For groundwater, this is going to be a lot higher, 5,270 years, with glaciers at about 12,000 years. Now, you can find these numbers by following this formula. Divide the total volume by the total flux in and out of those reservoirs. But some of this can make quite a bit of sense. So the atmosphere, of course, has such a short time because of all the cycling of it. The precipitation, water evaporates into the atmosphere, moves via wind movement, and then as those temperatures and environments change, it can get dropped as precipitation very readily again. That happens everywhere across the world. Surface water, while still fairly low, takes a little bit more time because it's the movement of that liquid water. There's a slower transit time as that liquid water has to actually physically flow across the surface. Then with the groundwater, you can see, with the oceans, you might expect that residence time to be a lot lower because of how much flux is going into and out of the ocean every year. But with the immense size of the ocean, it takes quite a bit of time, about 2,800 years, for water to really cycle into the ocean and then back out again. Groundwater is even slower because you have a lot lower fluxes. You have a lot smaller of a reservoir than the oceans, but that flux into and out of groundwater is going to be a lot slower. If you look back at table 1, the infiltration into groundwater is only about 2,000 cubic kilometers per year, and groundwater flow from groundwater into the ocean is about the same. So you don't really, that's a very small flux, especially compared to how much water is there. That's the 10.5 million cubic kilometers. So it takes some time for all that to go through. Glaciers, on the other hand, there is a very long time, our longest one, because of two things. That flux between in and out of glaciers it's actually not listed on. Okay, there we go. The flux into and out of the glaciers is 2,000 cubic kilometers per year. So a comparable flux to the groundwater, but the reservoir size is immense, almost over double. So whereas glaciers have about 25 million cubic kilometers of volume, groundwater only has about 10.5 million. So you have a similar flux for over twice the size, so that's why you have such a high residence time for the glaciers. And that also answers 21. Which reservoir has the shortest residence time? That's the atmosphere. Which has the longest? That would be glaciers. So the last few questions are on page 52, and I'm really just going to gloss through these a bit just because it's more about geometry than anything, but it's still important to understand this to a degree. So just for some review here, looking at the edge of the ocean and the continents, basically. So you have the deep ocean with an abyssal plain. That's the very flat portions of the ocean, kind of deep ocean. Then you have a continental rise and continental slope where you get that rise onto the continental crust. Then you have a continental shelf, which is pretty shallow, and before it goes back up again and is at the coast. So slope, of course, is a product of rise and run. Um, Looking at that last page of the lab manual for this exercise on page 52, as strange as it sounds, Antarctica is essentially a desert. The average yearly total precipitation is about 2 inches, yet 98% of the continent is covered with a thick, ancient sheet of ice. The average thickness of this ice is 8,000 feet with a maximum depth of nearly 3 miles. Overall, the mass of ice covers about 12 million square kilometers, which is 5.3 million square miles of the continent. The total amount of ice on Antarctica accounts for nearly 91% of all glacial ice on the Earth's surface. What would happen if the ice melted or entered the ocean, for instance, from extended global warming or from outward ice flow? In view of the vast size of the oceans, covering over 70% of the Earth's surface area, many people might at first think that the addition of ice or melted ice from the ice sheets would have little impact on global sea level. The numbers prove otherwise, however, and doing the calculations helps to instill this fact and help you recognize the vast size of the Earth's major ice sheet, the Antarctic ice sheet. 22. If the area of the world's oceans is approximately 361 million square kilometers, what would be the increase in the world's sea level? So, let's go back to this. Okay. 22. So for this one, what we're going to do is take that reservoir size. Give me just a moment. Let me pull up the key for this. It has all the math for it. That's the wrong one. All right, I can't seem to find the hydrology key here. So ultimately, if you do the math, let's look at so it gives us a depth of I don't have all my lab keys for this one, but effectively, if you take the volume of the glaciers, which is so 24 million cubic kilometers of the glaciers, and you melted that and added that all to the oceans based off of so if you add 24 million cubic kilometers of water to the 361 million kilometers of the square kilometers of the ocean, you would end up with about an 81 meter rise in sea level. That's insane. That would cover up huge areas of land. So for 23, the mean slope of the continental shelf is 1.9 meters per kilometer, or 0.0 degrees and 7 seconds. Every degree can be divided into 60 seconds. It's a weird method, but effectively 7/60ths of a degree. What that would mean is for every kilometer you travel in a horizontal direction, you move upwards 1.9 meters. So using that 81 meters, using that sea level change, how far inland would the water transgress, assuming a constant slope? Let's see if we have that. So a 1.9 meter rise over a, 1 kilometer or 1,000 meter run, how far up would that go? Basically, all you have to do here, divide 81 by 1.9 times 1,000. Just plug that into a calculator real quick. So 81, and my calculator died. So 81 divided by 1.9, multiply that by 1,000. And that's how many meters it would go inland. So that would go about 42 kilometers. 24. In some coastal areas, the slope of the land surface is smaller than the average continental slope. For example, between Memphis, Tennessee and the Gulf of Mexico, the slope along the Mississippi River is 0.15. So instead of 1.9, we get 0.15 meters rise for every 1,000 meter run. So let's do this again, but instead of 1.9, we'll do 1.5, 0.15. 81 divided by 0.15 times 1,000. So that would be about 540 kilometers inland. And for 25, which of the following cities would be underwater using the distance calculated from question 23? Which of the following cities would be underwater using the distance calculated in question 24? So it says to refer to one of the maps in the room to answer the question. I know we don't really have a map, but basically, if you just look at that 42 kilometer inland, let's say you have a continental slope of that 1.9 meters per kilometer, then that would basically sink Miami for sure. And that's about it from that list. However, with that more shallow slope of 0.15, that would end up sinking, of course, Miami, but that would also sink Atlanta, Georgia. That would sink Memphis. And that would also just about sink Little Rock, Arkansas. So with that more shallow slope, one of the lowest slopes you can find, that would flood a significant portion of the U.S. So this climate change, when you have all these glaciers melting, it actually can have significant damage to even just domestic environments, cities and places where people live. And while it might take a while for us to really observe this in the United States, there's all these different small islands around the globe, especially in the Southeast Pacific, where they're already suffering from some of this short rise. When you have a culture that lives on islands where the highest point is, 20 meters above sea level, a couple meters and uh, moving a kilometer or two inland on one of these small islands is going to cause massive changes in their lifestyle and huge damages to their society. So that is the Hydrologic Cycle Lab. If you have any questions, feel free to email me or talk to me after lab this week, and we can go from there. I hope you enjoyed this experience, and I hope you learned quite a bit about how the hydrologic cycle functions and how climate change can alter the environment.